Something is missing from our sky. Not something small, not something irrelevant, but an object we've been tracking for months. A visitor from beyond our solar system, a comet that crossed the void between stars to reach us, has entered a zone of complete silence. NASA's radars can't see it. Our most powerful telescopes are blind to its location. And as of October 21st, 2025, just yesterday, we lost our eyes on 3i Atlas exactly when it matters most. This isn't a malfunction. This isn't a technical glitch. This is physics, geometry, and timing converging into a moment of profound uncertainty that none of us, not the agencies, not the scientists, not you or me, were truly prepared to face. Because when you lose sight of something that doesn't belong to our cosmic neighborhood, something that traveled light years to get here, every second of silence feels like an eternity of unanswered questions. We live our lives assuming continuity. We expect the sun to rise, the seasons to turn, the objects we track to remain trackable. It's a comfort we rarely acknowledge until it's stripped away. And right now, on October 22nd, 2025, we're sitting in that uncomfortable space where continuity has been interrupted. Yesterday, 3i Atlas, the third confirmed interstellar object ever detected by humanity, slipped behind the sun from our perspective here on Earth. Not metaphorically, not in some abstract sense. Literally, it moved into what astronomers call solar conjunction, a geometric alignment where the comet, the sun, and Earth form a straight line, with the sun positioned directly between us and our target. From every ground-based telescope, from every radar installation, from every satellite pointed outward into space, the comet has become invisible, swallowed by the overwhelming glare of our star, hidden in a blind spot that physics itself has created. This isn't the first time we've experienced solar conjunction with celestial objects. Mars goes through it. Venus does. Even spacecraft like the Mars rovers endure communication blackouts lasting weeks when they pass behind the sun from Earth's viewpoint. We know this phenomenon. We've studied it. We've built our mission timelines around it. But knowing something intellectually and experiencing it emotionally, especially with an interstellar visitor, are two profoundly different things. Because this isn't Mars, a planet we've photographed thousands of times, whose orbit we've calculated down to the millisecond for decades. This is an object that originated outside our solar system, that followed a trajectory shaped by forces and events we can only speculate about, that arrived in our cosmic backyard carrying mysteries we've barely begun to unravel. And now, at the most critical phase of its journey, as it swings around the sun at its closest approach on October 29th, just 7 days from now, we can't see it. The silence feels different this time. Maybe it's because we've been watching 3i Atlas since its discovery earlier this year, building a relationship with this cosmic wanderer through data and observation. Maybe it's because every interstellar object we've encountered so far, Oumuamua in 2017, Borisov in 2019, and now this has carried surprises that challenged our assumptions about what these visitors should look like, how they should behave. Or maybe it's because, in a world where we've grown accustomed to instant information, real-time tracking, and satellites that can read license plates from orbit, the idea that something as significant as an interstellar comet can simply vanish from our instruments feels almost archaic, like a reminder of how small our technological reach really is against the scale of space. NASA and the European Space Agency knew this gap was coming. Orbital mechanics don't hide their intentions. Months ago, trajectory calculations predicted that 3i Atlas would enter solar conjunction in late October, creating an observational window that would close for approximately 2 weeks. Mission planners scheduled their observations accordingly, front-loading critical data collection to occur before the blackout, preparing follow-up campaigns for when the comet emerges on the other side of the sun in early November. This is standard procedure. This is how space science works, when you're dealing with objects moving at tens of thousands of miles per hour through a solar system where geometry constantly shifts. Nothing about the conjunction itself is unusual or unexpected from a technical standpoint. But here's what nags at the back of your mind. What keeps astronomers checking their email for updates, even though they know no new data will arrive? What if something changes during this gap? What if the close pass around the Sun, perihelion on October 29th, alters the comet in ways we can't predict? What if the intense solar radiation, the gravitational stress, the tidal forces trigger some transformation we won't witness because our eyes are covered by the sun's glare? Comets are volatile creatures. They're not solid rocks, but dirty snowballs, mixtures of ice and dust held together by weak gravity, responding dramatically to heat and pressure. When they approach the sun, they outgas, they fragment, they sometimes disintegrate entirely. And while we've seen dozens of solar system comets survive these close encounters, 3i Reckless isn't just any comet. It's an interstellar traveler, potentially forged in environments wildly different from our own stellar neighborhood, composed of materials that reflect the chemistry of another star system. The last confirmed observation came on October 20th, 2025. Multiple observatories contributed data, optical telescopes tracking its coma, spectrographs analyzing the gases streaming off its surface, astrometric instruments refining its position. Everything appeared normal. The comet was behaving as expected, following the trajectory calculated from months of prior observations, showing no signs of fragmentation or unusual activity beyond what we'd already documented. And then, within 24 hours, it crossed into the conjunction zone, and our instruments went blind. Not because they stopped working, not because we stopped looking, but because the sun, 864,000 miles in diameter and outputting more light than we could ever hope to filter out from ground-based or near-Earth telescopes, positioned itself as an impenetrable barrier. For those of us who remember a world before instant connectivity, before GPS satellites and weather apps that predict rain down to the minute, this moment might feel strangely familiar. There's an echo here of earlier eras when uncertainty was simply part of existence. When you sent a ship across the ocean and waited months to learn if it arrived safely, when travelers disappeared over horizons and you hoped they'd reappear on the other side. We've spent the last few generations eliminating those gaps, filling the voids with data and communication, building systems that promise complete knowledge and total visibility. And yet here we are, in October 2025, with all our technology and expertise, waiting in silence for a comet to emerge from behind the sun, trusting in orbital mechanics, but unable to verify, unable to observe, unable to do anything but calculate and hope our calculations are right. The gap is temporary. Let's be clear about that. By early November, 3i Atlas will have moved far enough from the sun's position in our sky that telescopes can reacquire it. Hubble has observation time scheduled. The James Webb Space Telescope will turn its infrared gaze toward the comet's new position. Ground-based observatories around the world have coordinated campaigns ready to activate the moment seeing conditions allow. Within weeks, we'll have fresh data, new images, updated trajectory information. The silence will end. The questions will start getting answers. This is a pause, not a conclusion. But pauses can be revealing. They force us to sit with our uncertainties, to acknowledge how much of our confidence comes from constant monitoring rather than complete understanding. Right now, we can tell you where 3i Atlas should be. Our gravitational models place it with impressive precision. We can predict when it should reappear in our instruments. We can estimate how its orbit will evolve after perihelion. Predict, estimate. These words carry confidence, but not certainty. And in that gap between the two, in that space where we're waiting for confirmation that our models match reality, something deeper stirs. A recognition that the universe doesn't owe us visibility, that there are moments when even our best efforts leave us watching an empty patch of sky, hoping for reemergence, wondering what we're missing while we wait. What if this silence isn't just hiding a comet's passage around the sun? What if, in these days when our instruments are blind, something more is happening, something the orbital equations can't predict, something the physics textbooks haven't prepared us for? That question sits uncomfortably in the mind, not because we have evidence pointing toward anything unusual, but because gaps have a way of breeding possibilities. And with an interstellar visitor, a cosmic stranger whose origins we can only infer, whose composition might differ from anything we've studied, whose behavior has already surprised us in subtle ways, with such an object, every moment of uncertainty feels heavier than it should. Before the silence descended, we knew quite a bit. 3 months of continuous observation had painted a portrait of 3i Atlas that was equal parts familiar and strange, comfort and confusion. From the moment of its discovery, earlier in 2025, observatories worldwide coordinated their efforts, gathering data across the electromagnetic spectrum, building a comprehensive dataset that would serve as our baseline for understanding this interstellar visitor. And what we learned in those months was that 3i Atlas behaves like a comet in most respects, but with peculiarities that kept researchers awake at night, running simulations and checking their instruments. The most dramatic encounter before the current gap occurred on October 3, 2025, when 3i Atlas passed within 95 million miles of Mars. In astronomical terms, this was a close approach, near enough that Mars orbiters, those robotic sentinels circling the red planet, equipped with cameras and spectrographs designed to study Martian weather and geology, could turn their attention skyward and observe the comet directly. These weren't Earth-based telescopes peering through hundreds of millions of miles of space, filtering through atmospheric distortion and light pollution. These were spacecraft in Mars orbit, with unobstructed views, sophisticated instruments, and the ability to track the comet over extended periods as it swept past their position. Initial data from those Mars observations showed 3i Atlas displaying an active coma, the cloud of gas and dust that surrounds a comet's nucleus as solar radiation heats its surface and causes ices to sublimate directly from solid to gas. This was reassuring in its normalcy. Comets are supposed to develop comas as they approach the Sun. It's what makes them visible from Earth, what creates those stunning tails that stretch across our skies. But the composition of that coma carried surprises. Spectrographic analysis, the technique where we split light into its component wavelengths to identify what elements and molecules are present, revealed something unexpected: significant amounts of nickel in the gas streaming off the comet's surface. Nickel, a heavy metal found in Earth's core, present in asteroids and meteorites, but not typically abundant in comets, or at least not abundant enough to show up prominently in spectroscopic observations. Normal solar system comets, the ones born in the Kuiper belt or Oort cloud surrounding our Sun, tend to release lighter elements and simple molecules: water vapor, carbon monoxide, carbon dioxide, ammonia, methane. These are the ices you'd expect from objects that formed in the cold outer reaches of a stellar system. Nickel appearing in such measurable quantities suggested something different about 3i Atlas's composition or formation environment. Then came the August 2025 observations from the James Webb Space Telescope, that engineering marvel positioned at the second Lagrange point, a gravitationally stable location beyond the Moon's orbit, where it could observe the universe with unprecedented infrared sensitivity. JWST turned its instruments toward 3i Atlas and detected carbon dioxide, TO2, outgassing from the comet, in amounts that seemed disproportionate to the water vapor release. Normal comets show a fairly predictable ratio between water ice and carbon dioxide ice, with water dominating by a significant margin because that's the most abundant volatile in our solar system's formation region. But 3i Atlas appeared to have relatively higher SeCO2 concentrations, suggesting it might have formed in a colder environment than our own comets, where carbon dioxide ice could remain stable rather than being depleted by radiation and heat over billions of years. These weren't devastating anomalies. They weren't observations that broke physics or demanded we rewrite our understanding of planetary science. But they were quirks, deviations from the template, hints that interstellar space, the realm between stars, where 3i Atlas spent potentially millions of years traveling, might have different chemical signatures than the Sun's gravitational domain. Every star system is slightly different. The elemental abundances, the initial conditions of the protoplanetary disk, the timing of planet formation, all these factors influence what kinds of comets and asteroids end up populating that system. 3I Atlas carried the fingerprints of another stellar environment, and we were seeing those differences manifest in its composition. Throughout September and early October 2025, additional observations refined our knowledge of the comet's physical characteristics. It appeared small by cometary standards, likely only a few hundred meters to perhaps a kilometer across its nucleus, though measuring the solid core beneath the glowing coma remains notoriously difficult, even with our best instruments. Its rotation seemed stable, no tumbling or chaotic spinning that might indicate recent fragmentation or collisions. The trajectory calculations grew increasingly precise, incorporating gravitational perturbations from Jupiter, Saturn, and even smaller influences from Uranus and Neptune as the comet fell deeper into the inner solar system. One number kept getting refined with each new observation: perihelion distance, the closest point to the Sun in the comet's orbit. As of October 20th, the last day before conjunction began, models placed perihelion at approximately 0.65 astronomical units from the Sun. That's 65% of the distance between Earth and the Sun, or roughly 60 million miles. For perspective, Mercury orbits at 0.39 AU, Venus at 0.72 AU. This meant 3I Atlas would be passing inside Venus's orbit, but outside Mercury's, experiencing solar radiation about 2.5 times more intense than what Earth receives, with temperatures capable of rapidly sublimating ices and potentially altering the comet's surface layers. And perihelion was calculated to occur on October 29, 2025, right in the middle of the conjunction gap, when we'd be blind to whatever happened during that closest approach. What we didn't see in those months of observation was equally important as what we did detect. There was no evidence of fragmentation, no secondary nuclei splitting off from the main body, no sudden outbursts of activity, suggesting structural instability. The comet appeared to be holding together well, despite the increasing solar heating as it approached the Sun. Its trajectory remained predictable, following the gravitational curves dictated by the Sun's mass and the orbital mechanics that govern all objects in space. No unexplained accelerations. No deviations that couldn't be accounted for by outgassing. The rocket effect, where jets of gas streaming off a comet's surface can subtly alter its path, something we've observed with many comets and even adjusted for with spacecraft navigation. But here's what sits in the back of every astronomer's mind as they review that pre-conjunction data: comets can be stable right up until they're not. We've watched comets survive dozens of passes around the Sun, only to suddenly disintegrate on what seemed like an unremarkable orbit. We've seen comets that looked robust in early observations break into multiple fragments as thermal stress cracked their structures. The tidal forces from a close solar passage, combined with the temperature extremes and the mechanical stress of rapid outgassing, can exceed a comet's structural integrity in ways that aren't always predictable from external observations. You can't measure internal cracks. You can't see the weak spots until they fail. So as 3I Atlas crossed into the conjunction zone on October 21st, astronomers had assembled a detailed portrait of an object that was mostly behaving as expected, with a few compositional quirks that made it interesting rather than alarming. They had trajectory data accurate enough to predict its position months into the future. They had spectroscopic signatures that told stories about its origin in another star system. They had documented its activity patterns, its coma development, its response to solar heating. In scientific terms, they had done their homework, checked their instruments, and prepared for the observational gap they knew was coming. But preparation doesn't eliminate unease, especially when the last data point comes just before the most critical phase of the comet's journey, just before perihelion, just before the moment of maximum stress and maximum change. What we knew before the gap was substantial. What we'll learn after the gap remains to be seen. And in between sits this moment of enforced patience, where the only thing we can do is trust our calculations and wait for geometry to favor us again. for the Earth's rotation around the Sun to carry us to a position where 3I Atlas emerges from behind our star's glare, visible once more, hopefully unchanged, hopefully predictable, hopefully just a comet doing what comets do when they visit the inner solar system. Hopefully, but what if the perihelion passage, that closest approach happening right now, today, October 29th, hidden behind the Sun, changes everything we thought we understood? Understanding why we can't see 3I Atlas right now requires understanding something fundamental about how we observe the cosmos. Our telescopes, no matter how powerful, are limited by one simple fact: they collect light. Everything we know about distant objects, their composition, motion, temperature, even their existence, comes from photons that traveled across space to reach our instruments. And when an object moves behind the Sun, from our perspective, those photons can't reach us anymore. Not because the object stopped emitting or reflecting light. Not because our instruments failed, but because an 864,000 mile diameter ball of incandescent plasma positioned itself directly in our line of sight, outputting so much light that it drowns out everything in its vicinity, like a spotlight shining directly into your eyes in a dark room. This is solar conjunction. It happens with predictable regularity to any object whose orbit carries it to the far side of the Sun from Earth's perspective. For inner planets like Venus and Mercury, these conjunctions are brief, lasting days or perhaps a couple weeks depending on the geometry. For Mars, which orbits outside Earth's path, solar conjunction can last a month or more when the two planets are on opposite sides of the Sun and our star sits directly between. We've dealt with this limitation since humans first pointed instruments at the heavens. Ancient astronomers noted how planets would disappear and reappear from observation. Medieval stargazers marked these periods as times of astronomical blindness. Modern space agencies build entire mission schedules around avoiding critical operations during conjunction blackouts. But knowing the physics doesn't make the experience any less frustrating, especially now, in an era where we've grown accustomed to continuous observation, to satellites that never blink, to spacecraft that send back data 24 hours a day. The idea that we simply have to wait, that no amount of money or technology can let us see through the Sun's glare to spot a comet on the other side, feels almost primitive, and yet here we are, waiting. The geometry is straightforward. As of October 21st, 2025, Earth, the Sun, and 3I Atlas formed a line with the Sun in the middle. From our vantage point on Earth, any attempt to observe the comet meant pointing our telescopes toward the Sun, or at least toward a region of sky so close to the Sun that its overwhelming light contaminated everything. Even space-based telescopes like Hubble, which orbit above Earth's atmosphere and can observe without atmospheric interference, can't look directly at or near the Sun without risking permanent damage to their sensitive instruments. The solar radiation is simply too intense. The contrast between the Sun's brightness and any nearby object too extreme for conventional imaging systems to handle. There's a narrow exception to this blackout: specialized solar observatories. Satellites like GOES-19, positioned in geostationary orbit and equipped with coronagraphs, instruments that use a disk to physically block the Sun's direct light, can potentially observe objects passing very close to the Sun in their field of view. These satellites are designed to study the Sun's corona, that tenuous outer atmosphere that extends millions of miles into space and becomes visible during total solar eclipses. By blocking the Sun's photosphere, coronagraphs can detect fainter objects near the solar disk. And in theory, if 3I Atlas passes through the right region of sky during conjunction, these instruments might catch a glimpse. But coronagraph observations come with limitations. The field of view is narrow, focused on the immediate solar vicinity. The instruments are optimized for detecting diffuse coronal structures and solar wind phenomena, not compact comets. And even if 3I Atlas appears in the right place at the right time, what we'd see is a brief snapshot, a position confirmation, perhaps a rough brightness estimate. but not the detailed spectroscopy and long-duration tracking that lets us analyze composition and trajectory with precision. It's the difference between seeing someone walk past a window and sitting down with them for a conversation. Both are forms of observation, but only one gives you real information. So for approximately 2 weeks, bracketing October 29th, perihelion day, we're effectively blind to 3i Catlus's condition and behavior. We know where it should be based on gravitational calculations. We can model its expected trajectory with software that accounts for the sun's gravity, the subtle perturbations from planets, even the slight push from solar radiation pressure on the comet's coma. These models are sophisticated, tested against decades of observations of other comets and asteroids, refined to account for every known force acting on objects in the solar system. They tell us that 3i Atlas will swing around the sun at a distance of approximately 60 million miles on October 29th, gaining velocity as it falls into the sun's gravitational well, a phenomenon called the Oberth effect, where performing maneuvers or experiencing acceleration at the lowest point of an orbit produces maximum energy change. The Oberth effect matters here because it means perihelion is the moment of maximum velocity for 3i Atlas. The comet is moving faster through space today than it ever has during its journey through our solar system, racing around the sun at speeds exceeding 100,000 miles per hour relative to our star. This isn't science fiction propulsion. It's simply gravitational physics. Objects accelerate as they fall toward massive bodies, then decelerate as they climb back out of the gravity well. But that burst of speed, combined with the close solar approach, subjects the comet to intense tidal forces. The side facing the sun experiences slightly stronger gravity than the far side, creating a stretching effect that can stress a comet's structure. For a loosely bound collection of ice and dust, this can be catastrophic if the internal strength can't withstand the differential forces. Will 3i Atlas survive perihelion intact? Almost certainly yes, based on what we know about its structure and the fact that the closest approach stays well outside the Roche limit, the distance at which tidal forces overcome an object's self-gravity and tear it apart. At 60 million miles, the tidal stress is real but manageable for a typical cometary nucleus. We're not expecting disintegration. But expecting isn't the same as observing. We've been surprised before by comets that fragmented under conditions that seemed survivable, their internal weaknesses hidden until thermal and mechanical stress exploited them during perihelion passage. And then there's the outgassing question. As solar heating intensifies approaching perihelion, ices sublimate more rapidly, gases stream off the surface in greater volume, the coma expands and potentially develops more prominent tails. This is normal comet behavior, but for an interstellar visitor whose composition shows those nickel and carbon dioxide peculiarities, how will the outgassing pattern evolve under peak solar radiation? Will new volatiles emerge from freshly exposed surface layers as outer material sublimates away? Will the activity become more vigorous, producing jets and streamers visible in post-conjunction observations? Or will something unexpected happen? A compositional surprise waiting in the nucleus interior, revealed only when the outer layers get stripped away by solar heat. These aren't idle speculations. They're the questions that keep planetary scientists refreshing their inboxes, checking for early reports from solar observatories, running simulations on their computers to predict what conditions the comet is experiencing right now behind the sun's glare. Because while we can't see what's happening, we can model it. We can calculate the temperature at the comet's surface, estimate sublimation rates, project how much mass is being lost to outgassing, assess whether structural integrity should hold. The models say everything should be fine. The models say 3i Atlas will emerge from conjunction intact, perhaps slightly more active due to the perihelion heating, but fundamentally unchanged. The models have been reliable for decades of solar system comet observations. But models are built on data from objects that formed in our stellar neighborhood. They're calibrated against comets born in the Kuiper belt or Oort cloud, shaped by the sun's radiation and the specific mix of elements present when our solar system condensed from its protoplanetary nebula 4.6 billion years ago. 3I Atlas formed somewhere else, under potentially different conditions, from materials that might not match our templates exactly. Those compositional quirks we detected, the nickel, the elevated carbon dioxide, hint at differences we haven't fully characterized. And differences, even small ones, can matter during extreme events like perihelion passage. What if the thermal response is different? What if the structural strength isn't what we assumed? What if some element of the comet's makeup produces unexpected behavior under the intense solar radiation and tidal stress it's experiencing today? We won't know until early November, when Earth's orbital motion carries us to a position where 3I Atlas emerges from the sun's glare into observable sky. Telescopes will reacquire it. Spectrographs will analyze its coma. Astrometric measurements will confirm whether its trajectory matches predictions. Within days of reappearance, we'll have answers to most of the immediate questions. But between now and then, we sit in this blind spot that physics has created, trusting orbital mechanics, trusting our models, trusting that the universe behaves the way our equations say it should. Most of the time, that trust is rewarded. The universe is lawful. Gravity doesn't change its rules. Thermodynamics remains consistent. Objects follow predictable paths through space unless acted upon by external forces we can measure and account for. This is the foundation of modern astronomy. The confidence that what we observe today will connect logically to what we observe tomorrow, that gaps in observation are just temporary interruptions in an otherwise continuous narrative. And yet, in the back of your mind, there's this whisper: what if something in that gap changes the story? What if, during these days when we're blind, the ordinary becomes extraordinary in ways we can't predict because we've never seen an interstellar comet go through perihelion before? What if the silence is hiding not just a continued orbit, but a transformation? That question will have to wait for an answer. For now, the blind spot persists, and all we can do is calculate, model, predict, and prepare for the moment when visibility returns, and we discover whether our confidence was justified or whether the universe had a surprise waiting for us behind the sun's glare. Let's be methodical. Let's examine every mundane reason why 3I Atlas might not reappear as expected when the conjunction ends. Because before we allow our minds to wander toward extraordinary explanations, we owe it to ourselves and to the scientific method to systematically work through the ordinary possibilities, the natural explanations that would require nothing unusual, nothing unprecedented, nothing that violates our understanding of how comets behave when they visit the inner solar system. This is how science progresses, not by jumping to spectacular conclusions, but by eliminating simpler alternatives first, by building cases carefully from evidence rather than speculation. The most straightforward explanation for a post-conjunction absence would be complete fragmentation and dispersal. Comets do break apart. We've witnessed it dozens of times. Comet Shoemaker-Levy, 9 famously shattered into more than 20 pieces before those fragments slammed into Jupiter in 1994, creating massive impacts that taught us volumes about both cometary composition and Jupiter's atmosphere. Comet Linear disintegrated in 2000 as it approached the Sun, breaking into a stream of small fragments that quickly dispersed beyond detectability. More recently, comets like Atlas C Ca 2019Y4 fragmented in 2020, initially appearing as a brightening object before observations revealed it was breaking apart, its nucleus unable to withstand the thermal and mechanical stress of solar approach. Could 3I Atlas have suffered the same fate during perihelion on October 29th? Structurally, it's possible. Comets are not solid rocks but aggregations, loose collections of ice, dust and rock held together by weak gravity and the sintering effect, where ices fuse together in the cold of space. Think of them as cosmic dirt clods rather than boulders. When solar heat sublimates the ices that act as binding material, when outgassing creates internal pressure that pushes outward against already weak structure, when tidal forces pull harder on the near side than the far side, A comet can simply come apart. The fragments disperse along the original orbit, spreading out over time into a stream of debris that becomes progressively harder to detect as each piece gets smaller and fainter. But here's the problem with applying this explanation to Three-Eyed Atlas. We had no warning signs. In the months leading up to conjunction, observations showed a stable nucleus, consistent activity patterns, no evidence of splitting or unusual outbursts. Comets that fragment typically show precursor behavior. Sudden brightness increases as fresh material gets exposed, or the appearance of secondary condensations in the coma, indicating pieces separating from the main nucleus. These signs usually appear days to weeks before major fragmentation events, giving observers warning that structural failure is imminent. Three-Eye Atlas displayed none of these indicators through October 20th. Moreover, the perihelion distance of 0.65 AU, while close, isn't unusually stressful by cometary standards. Many comets pass closer to the Sun and survive. The famous Kreutz family of sun-grazing comets swings within a few solar radii of the Sun's surface, experiencing temperatures hot enough to vaporize rock, yet many of these objects survive their extreme perihelion passages intact. At 60 million miles, Three-Eye Atlas is experiencing significant solar heating, but nothing that should automatically doom a reasonably consolidated comet nucleus. The temperature at its surface today is probably around 350 400 Kelvin, hot enough to rapidly sublimate water ice and carbon dioxide ice, but not hot enough to melt rock or vaporize more refractory materials. Still, there's an uncertainty factor. We don't know. Three-Eye Atlas's exact structural integrity. We've only observed it from the outside, inferring properties from its brightness, its spectral signature, its outgassing patterns. Internal structure, whether it's a monolithic chunk or a loosely aggregated rubble pile, whether it has hidden cracks or void spaces, whether the material distribution is uniform or layered, all of this remains unknown because we can't send a spacecraft to examine it up close. An internal structure determines how well an object withstands stress. A solid nucleus might shrug off tidal forces that would tear apart a loosely bound aggregate. We're making educated guesses based on statistical samples of other comets, but each comet is an individual with its own formation history and structural characteristics. So complete fragmentation remains a possibility, albeit one that would surprise most researchers given the pre-conjunction observations. If Three-Eye Atlas has fragmented, we'll discover this in early November when searches in the predicted location find nothing. No primary nucleus, no bright coma, just perhaps a diffuse cloud of dispersing material or even emptiness, if the fragments have spread too far to detect. This would be scientifically valuable in its own way, telling us that interstellar comets can be more fragile than their solar system counterparts, that the journey through interstellar space might compromise structural integrity in ways we haven't previously considered. Another natural explanation involves trajectory change. Comets can experience non-gravitational forces from outgassing, essentially using their own sublimating ices as a weak rocket engine. When gas jets erupt from a comet's surface, they carry momentum, and by Newton's third law, they impart an opposite momentum to the nucleus itself. For a small object, like Three-Eye Atlas, with low mass and strong outgassing, these non-gravitational forces can produce measurable trajectory changes over weeks and months. We've observed this with many comets, and even factor it into our trajectory predictions when we have enough data to characterize the outgassing patterns. But what if perihelion triggered unexpectedly vigorous outgassing, producing non-gravitational forces larger than our models predicted? What if the trajectory change is significant enough that Three-Eye Atlas won't be where we expect it to be in early November, causing initial searches to miss it entirely until we expand the search area? This wouldn't mean the comet vanished in some mysterious way, just that it moved farther off the predicted path than our error bars anticipated, requiring more time to relocate. This explanation has precedent. Comet 17P/Holmes famously underwent a massive outburst in 2007, brightening by a factor of 500,000 in less than 24 hours. as some internal event triggered explosive outgassing. The comet survived, but its trajectory was measurably affected by the force of that eruption. If something similar happened to 3I Atlas during perihelion, perhaps triggered by the sudden exposure of a particularly volatile rich layer, as surface material sublimated away, the resulting trajectory change could complicate reacquisition. Yet again, we face the problem of plausibility. Outgassing forces large enough to significantly alter a comet's trajectory in just a few days would almost certainly produce a dramatically brightening coma visible even at a distance. We'd expect this to potentially show up in wide-field sky surveys or even amateur astronomer observations as an unexpectedly bright object appearing in an unusual position. While the conjunction makes direct observation impossible, there are automated surveys continuously photographing large sections of sky, and a brightening 3I Atlas outside its predicted location might be detectable to these systems depending on its brightness and position. As of now, no such reports have emerged, though it's early yet, and search campaigns are just beginning to ramp up as the conjunction window closes. Then there's the mundane possibility that 3I Atlas simply became too faint to detect. Comets vary dramatically in brightness depending on their activity levels. If the perihelion passage actually reduced outgassing rather than enhancing it, perhaps by sealing the surface with a crust of non-volatile material left behind, as ices sublimate, a phenomenon we've observed with some comets, 3I Atlas might reappear much dimmer than expected, below certain brightness thresholds. Even large professional telescopes struggle to detect objects against the background stars and galaxies. A comet that faded significantly would require longer exposure times, more sensitive instruments, and careful analysis to distinguish from background noise. This seems unlikely for a comet fresh from perihelion, since solar heating typically enhances rather than suppresses activity, but cometary behavior has surprised us before. Some comets show unexpected brightness drops after perihelion, their surfaces undergoing changes that reduce gas and dust production. If 3I Atlas falls into this category, detection might be delayed not because it vanished, but because it became harder to see, requiring more observation time before confident detection. Each of these natural explanations, fragmentation, trajectory deviation, brightness reduction, offers a straightforward way to account for a post-conjunction absence without invoking anything unusual. They're grounded in observed cometary behavior, supported by decades of precedent with solar system comets. Scientists will be systematically testing these hypotheses starting in early November. Search campaigns will scan the predicted position and surrounding regions of sky with increasing radius to account for possible trajectory errors. Deep exposure imaging will probe for faint objects that might represent a dimmed nucleus. Infrared observations might detect warm material even if visible light emission is weak. The searches will be thorough, methodical, and comprehensive. But here's what keeps nagging at the informed observer. 3I Atlas isn't a typical comet. It's the third confirmed interstellar object ever detected, part of a population we've barely begun to characterize. The first interstellar visitor, Oumuamua, exhibited acceleration inconsistent with observed outgassing, spawning years of debate about whether it represented something other than a simple comet or asteroid. The second, Borisov, appeared more conventionally comet-like, but still carried compositional surprises. Now 3I Atlas brings its own quirks, that nickel signature, the carbon dioxide enrichment, the retrograde orbit that's statistically unusual. Each interstellar object has reminded us that our templates, built from solar system examples, might not fully capture the diversity of what exists in the broader galaxy. So while the ordinary explanations are plausible and deserve to be tested first, there's this background awareness that with interstellar visitors, ordinary might not be the whole story. The question isn't whether natural explanations exist. They clearly do. The question is whether nature followed one of our expected scripts, or whether perihelion revealed something about 3-eyed Atlas that doesn't fit neatly into our categories. We won't know until we look, and we can't look until the conjunction ends, until geometry favors us again, until Earth's rotation around the Sun carries us to a vantage point where the comet's predicted location becomes visible once more. Every scientist working on 3i Atlas right now is hoping for the ordinary, hoping the comet reappears right where it should be, perhaps a bit more active from the perihelion heating, its trajectory matching predictions within expected error margins. That would be the clean outcome, the one that confirms our understanding and lets research continue without complications. But hope and expectation aren't the same as observation. And until those early November observations confirm the ordinary, there's room in the mind for wondering whether the silence is hiding something we haven't accounted for, something that would require explanations we haven't yet seriously entertained. Which brings us, carefully and deliberately, to the realm of the extraordinary, not as confirmed truth, but as possibilities we owe ourselves the intellectual honesty to examine. We need to talk about the rumors, the speculation, the whispers circulating in corners of the internet, and occasionally even crossing through professional channels before being quickly dismissed or contextualized. Because when something as significant as an interstellar comet enters a blind spot at the most critical phase of its journey, when the observational gap happens to coincide with perihelion, when the object in question has already shown compositional oddities, human nature being what it is, speculation emerges. Some of it is grounded in genuine scientific curiosity about edge cases and unlikely scenarios. Some of it reflects deeper psychological needs to find patterns and meaning in uncertain situations. And some of it, frankly, is the product of misunderstood information getting amplified through social media until it bears little resemblance to the original context. Let's start with the most prominent speculation, the one carrying a name that commands attention in certain circles. Avi Loeb, professor at Harvard, chair of the astronomy department, prolific researcher in areas ranging from black holes to the search for extraterrestrial intelligence. And yes, the scientist who argued that Oumuamua, the first interstellar object detected in 2017, might have been a piece of alien technology rather than a natural asteroid or comet. That hypothesis generated enormous controversy, split the astronomical community, and made Loeb simultaneously famous to the public and somewhat controversial among peers who felt he was overinterpreting limited data. In July 2025, according to various online sources and some second-hand reports, Loeb allegedly made comments about 3i Atlas suggesting the possibility, and we need to emphasize possibility, speculation, hypothesis rather than conclusion, that the object might represent artificial technology, perhaps even under some form of intelligent control. The reasoning, if these reports accurately captured his thinking, centered on those compositional anomalies, the nickel detection, the carbon dioxide ratios, and potentially other spectroscopic features that didn't quite match the standard cometry template. Nickel alloys are, after all, commonly used in engineering applications. Metal-rich compositions aren't what we expect from dirty snowballs. Could this indicate something manufactured rather than naturally aggregated? Here's where we need to pump the brakes and inject some rigorous honesty into the narrative. First, these reports of Loeb's comments are largely unverified in the sense that they haven't appeared in peer-reviewed publications, official press releases from Harvard, or statements released through institutional channels where they'd carry scientific weight. They've circulated through social media, appeared in speculative blog posts, been referenced in YouTube videos exploring fringe theories. This doesn't automatically make them false. Loeb has been publicly vocal about considering technological explanations for unusual astronomical objects, but it means we're dealing with rumor and interpretation rather than documented scientific claims. Second, and more importantly, the nickel detection that supposedly underpins this speculation has a perfectly mundane explanation that actually reinforces 3i Atlas being a natural comet. Nickel in cometry spectra isn't unprecedented. In fact, multiple research teams in 2021 published findings showing that nickel and iron atoms had been detected in the coma of comets observed from Earth, and even in the coma of the interstellar comet Borisov. The presence of these metals appears to be more common than previously recognized, likely released when dust grains containing metallic components get heated by the sun and release these atoms in gaseous form. It's not evidence of artificial composition, but rather evidence of better spectroscopic instruments detecting features we couldn't measure a generation ago. Similarly, the elevated carbon dioxide levels, while interesting from a comparative planetology perspective, don't require exotic explanations. Different formation environments produce different ice ratios. A comet that formed farther from its parent star in a colder region would naturally retain more carbon dioxide relative to water compared to a comet from a warmer formation zone. This tells us something about 3I Atlas's origin system. Perhaps it formed around a dimmer star, or farther out in that system's equivalent of the Kuiper belt, but it doesn't imply anything non-natural. So if the compositional features have natural explanations, why does the speculation persist? Part of it is the inherent ambiguity of remote observation. We can't land on 3I Atlas. We can't collect samples. We can't examine its structure directly. Everything we know comes from light. Photons that traveled across space and got collected by our instruments, then analyzed through spectroscopy and photometry and astrometry. And while these techniques are remarkably powerful, revealing chemical compositions and physical properties across vast distances, they leave room for interpretation, especially when dealing with objects whose formation history differs from our local sample. There's also the pattern recognition factor. When Oumuamua exhibited that unexplained acceleration, when it tumbled in ways that seemed inconsistent with typical cometary outgassing, when it showed no obvious coma despite passing through the inner solar system, where solar heating should have triggered outgassing, those anomalies prompted technological hypotheses. Now we have a second interstellar visitor with its own set of quirks, and pattern-seeking minds naturally wonder, is this a trend? Are interstellar objects systematically different in ways that might indicate something beyond natural processes? 3 data points, Oumuamua, Borisov, and 3I Atlas, aren't enough to establish robust statistics, but they're enough to fuel speculation. Then there are the more exotic claims floating around less credible sources, reports of radio signals detected from 3I Atlas's vicinity, allegations of unusual spectral lines suggesting exotic materials, claims that government agencies have detected something anomalous but aren't publicly disclosing it. These need to be addressed, not because they're likely true, they're almost certainly not, but because they're part of the information environment surrounding this event, and people encountering them deserve context for evaluating such claims. Radio signals from comets are actually normal. Comets produce natural radio emissions through several mechanisms: plasma interactions between the solar wind and the comet's coma, electron impacts on cometary molecules, even thermal emissions from warm dust. Radio telescopes regularly detect emissions from bright comets without invoking anything artificial. If 3I Atlas produced detectable radio emissions during its active phase approaching perihelion, this would be interesting scientifically, but not anomalous. What would be anomalous is a structured signal, narrowband emission at specific frequencies, showing patterns inconsistent with natural sources, perhaps modulation that implies information encoding. No credible reports of such signals from 3I Atlas exist in scientific literature or official observatory announcements. The alleged exotic spectral lines face similar scrutiny. Every element and molecule has a unique spectral signature, specific wavelengths where it absorbs or emits light. A century and a half of spectroscopy has catalogued these signatures extensively. Unknown lines occasionally appear in astronomical spectra, but they virtually always turn out to be either instrumental artifacts, terrestrial atmospheric contamination, or known substances in unusual excitation states that shift their spectral features slightly. The idea that 3I Atlas shows spectral lines from materials unknown to science is extraordinary enough to require extraordinary evidence, and no such evidence has been presented through credible channels. As for government secrecy theories, these reflect misunderstandings about how modern astronomy operates. Astronomical data comes from distributed networks of observatories, university facilities, international collaborations, amateur astronomers, space telescopes, with observation schedules planned months in advance, and publicly accessible data archives. The transparency is built into the system. Yes, there are data release delays, typically months or even a year or two for major missions to give the science teams first crack at analysis before public release. But covering up something significant about an object being watched by hundreds of independent observers worldwide would require a conspiracy spanning multiple nations, institutions, and thousands of individuals, with perfect operational security preventing any leaks. This strains credibility to the breaking point. So why give any attention to these speculations at all, if they're unsupported? Because ignoring them doesn't make them disappear, and pretending they're not part of the conversation around 3i Atlas is dishonest. People hear these rumors. They encounter sensational headlines. They see YouTube thumbnails with dramatic implications. And if we're going to help anyone think clearly about what's happening, we need to acknowledge the speculation exists while simultaneously providing the context that shows why mainstream science hasn't embraced these extraordinary claims. More importantly, there's value in considering even unlikely scenarios as thought experiments, as long as we're clear about their speculative nature. What if an interstellar object did exhibit features inconsistent with natural formation? How would we recognize it? What observations would constitute convincing evidence versus mere curiosity? These questions aren't irrelevant. They're part of the framework for how we'd approach genuine anomalies if they ever appeared. Organizations like SETI, Search for Extraterrestrial Intelligence, have protocols for this, criteria for evaluating whether a signal or observation might represent technology rather than nature. Those criteria are strict, requiring multiple independent confirmations, exhaustive elimination of natural explanations, and peer review before any extraordinary claims get made. 3i Atlas doesn't meet those criteria. Its features, while interesting, all have plausible natural explanations. Its trajectory follows gravitational predictions without requiring propulsion. Its spectroscopic signature matches cometary composition with regional variations consistent with different formation environments. It's behaving like a comet, looking like a comet, and requiring nothing beyond standard physics to explain. The fact that we can't currently observe it due to solar conjunction doesn't change this baseline assessment. But here's the subtle point that's worth sitting with: our inability to observe doesn't change the assessment, but it does prevent us from updating that assessment with new data. If something were happening during perihelion that challenged our natural explanations, if outgassing patterns became truly bizarre, if trajectory changes defied gravitational models, even accounting for reasonable non-gravitational forces, if spectroscopic signatures shifted in ways incompatible with thermal and radiation effects, we wouldn't know about it yet. The conjunction creates not just an observational gap, but an information gap, a period during which our confidence in the object's nature is frozen at the last good observation rather than continuously updated, as would normally occur. This doesn't mean we should assume something extraordinary is occurring. The vastly most likely scenario remains that 3i Atlas is doing exactly what our models predict, heating up at perihelion, outgassing more vigorously, perhaps shedding some surface layers, following its gravitational trajectory around the Sun, preparing to emerge from conjunction as a slightly more weathered but fundamentally unchanged comet. Extraordinary claims require extraordinary evidence, and we have no such evidence. What we have is absence of information, and absence of evidence isn't evidence of absence, but it's also not evidence of anything in particular. The responsible position is to note the speculation exists, explain why it's not currently supported by data, and wait for observation to resume, which it will, starting in early November, when dozens of telescopes will turn toward the predicted position of 3i Atlas and either confirm the ordinary or, far less likely but theoretically possible, detect something that demands a deeper rethinking of what we assumed about this visitor from interstellar space. Until then, speculation remains speculation, rumor remains rumor, and the scientific process continues its methodical work of gathering data, testing hypotheses, and following evidence wherever it leads, even if, for a few weeks in October 2025, we have to follow it blind, trusting our instruments and our models, until geometry allows us to see again. And if there's a sliver of excitement in that waiting, a small acknowledgement that the universe has surprised us before and might yet do so again, that's not unscientific. That's human. As long as we don't mistake excitement for evidence or speculation for conclusion, there's room in the mind for both rigorous skepticism and a carefully guarded sense of wonder at what might be learned when the silence ends. When something unusual happens in space, when an object goes off the radar or exhibits unexpected behavior, people naturally look to the authorities for explanation and reassurance. NASA, the European Space Agency, the various national space programs and international astronomical organizations, these institutions carry weight, represent expertise, and are expected to provide clear communication about cosmic events that might affect or at least interest the public. So what have they said about the current 3I Atlas situation? What messages have come from official channels about the conjunction, the perihelion passage, the temporary loss of observation? And perhaps more significantly, what haven't they said? And what does that silence mean? The official statements from NASA regarding 3I Atlas have been, to put it mildly, minimal. The agency's online resources mention the comet in passing, noting its interstellar origin and providing basic orbital parameters through the JPL Small Body Database, a catalogue of asteroids, comets, and other small objects tracked by NASA's Center for Near-Earth Object Studies. These database entries get updated as new observations refine trajectory calculations, but they're technical resources aimed at researchers rather than public communications. There's no press release announcing the conjunction, no public advisory about the observational gap, no reassuring statement that everything is proceeding normally and the comet will be reacquired in November. Just technical data, accessible to those who know where to look but not exactly designed for public consumption or engagement. The European Space Agency's communications have been similarly restrained. ESA coordinates observations from European facilities and has been involved in 3I Atlas research through collaborations with member state observatories, but public-facing statements have been scarce. Some data appears in technical reports accessible through ESA's scientific archives, documenting observations made before the conjunction, but again, these are specialized resources rather than broader communications. Is this silence unusual? Is it concerning? To answer that, we need to understand how space agencies typically handle communication around astronomical events. For objects that pose potential hazards, near-Earth asteroids whose orbits might bring them uncomfortably close to our planet, NASA maintains active public communication, providing regular updates on trajectory calculations, impact probabilities, and mitigation strategies if needed. The threat assessment drives the communication priority. But 3I Atlas poses no hazard. Its orbit passes nowhere near Earth at any point in its journey through the solar system. From a planetary defense standpoint, it's entirely non-threatening. For scientifically interesting but non-hazardous objects, communication patterns depend on available resources, competing priorities, and public interest levels. Space agencies field thousands of observations annually. Their public affairs officers manage communications about missions, discoveries, and events, but they can't issue detailed press releases for every interesting comet or asteroid. Choices get made about what warrants broad public communication versus technical documentation for the scientific community. In that framework, 3I Atlas, as interesting as it is to researchers, falls into a category that gets technical coverage without major press events, unless something truly extraordinary emerges from the observations. But here's where the silence gets interesting. We're not just dealing with another comet. This is an interstellar visitor, only the third ever confirmed arriving during an era of heightened public interest in space exploration, extraterrestrial possibilities, and astronomical phenomena. The previous interstellar objects generated significant media coverage and public engagement. Oumuamua became a household name in certain circles. Borisov was covered extensively in science news. You'd think Three-Eye Atlas would warrant at least similar attention, particularly given the dramatic timing of its conjunction coinciding with perihelion. And yet, the institutional communications have been remarkably muted. Several explanations exist for this communication gap. First, timing October 2025 coincides with various organizational challenges within space agencies. Government agencies have dealt with budget negotiations, administrative transitions, and resource allocation issues that can delay non-critical communications. Science communication staff are stretched thin, managing multiple priorities. A comet that's temporarily unobservable might simply fall lower on the priority list than missions with active operations requiring public engagement. Second, there's the data availability issue. When the object of interest is hidden behind solar conjunction, there's literally nothing new to report. Observation data flow has stopped. The last meaningful update came on October 20th, before conjunction began. Without fresh data, public affairs teams have little to communicate beyond "we're waiting for the conjunction to end," which doesn't make for particularly compelling press releases. Why issue statements about an observational gap when the gap itself is routine and temporary? Third, institutional caution plays a role. The space agencies are acutely aware that their statements carry authority and can spark public reactions. If they highlight the conjunction gap and the temporary invisibility of Three-Eye Atlas, they risk feeding speculation and concern without providing corresponding reassurance, since they can't show new observations proving everything is fine until November. The cautious choice might be saying little rather than saying something that generates more questions than answers. But acknowledging these practical explanations doesn't entirely eliminate the nagging sense that something feels off about the communication posture around this event. We've seen space agencies masterfully handle science communication around complex missions, explaining technical details in accessible language, building public enthusiasm for discoveries, managing expectations during observational campaigns. Why not apply similar communication energy to an interstellar visitor going through its closest solar approach? Why leave the information field to speculation and rumor, rather than proactively shaping public understanding? One possibility, though difficult to prove without insider access, is that institutional priorities have shifted regarding interstellar objects. After the Oumuamua controversy, where the debate over whether it might be artificial technology garnered enormous media attention, much of it sensational, agencies might have decided that more restrained communication serves the science better. Let the observations accumulate. Let peer review work. Don't fuel speculation with preliminary data or highlight anomalies that might have mundane explanations but could get misinterpreted by media hungry for sensational angles. Keep it technical. Keep it conservative, and communicate firm conclusions rather than tentative observations. There's also the Mars observation complication. Remember that Mars orbiters observed Three-Eye Atlas during its October 3rd flyby past the red planet. That data was supposed to provide high-quality close-up information about the comet's structure and composition. But as of late October 2025, full analysis and public release of that Mars data has been delayed. Some reports attribute this to administrative issues within US government agencies dealing with data processing and release approvals. Others suggest computational analysis is taking longer than anticipated. Either way, potentially valuable information from those Mars observations remains unpublished, creating another gap in the public knowledge base. These delays, while frustrating, aren't unprecedented. Science operates on timescales that often frustrate those accustomed to instant information. Data needs calibration, analysis needs peer review, conclusions need verification before they're released to avoid spreading misinformation. The scientific process is deliberately slow and cautious, which conflicts with our contemporary expectation of real-time updates. But the combination of the Mars data delay and the general communication silence around Three-Eye Atlas creates an information vacuum that speculation naturally fills. What about the planned observations for November and December 2025? Here the agencies have been more forthcoming, at least in technical scheduling documents. Hubble Space Telescope has observation slots allocated for 3I Atlas in mid-November, timed for when the comet emerges from conjunction into favorable viewing geometry. The James Webb Space Telescope has infrared observation campaigns planned. Multiple ground-based observatories have coordinated time reserved. These schedules appear in public databases accessible to the astronomical community, signaling that official interest remains high even if public communications have been minimal. This is arguably where institutional actions speak louder than words. The fact that premier observational resources, Hubble and JWST time, is incredibly competitive, oversubscribed by factors of 10 or more, have been dedicated to 3I Atlas follow-up observations, indicates the scientific community judges this object worthy of significant attention. If researchers believed there was nothing unusual or particularly interesting to study, they wouldn't be competing for these observation slots. The resource allocation reflects genuine scientific priority, even if the press releases haven't materialized. So what should we make of the institutional silence? Is it routine resource management and communication prioritization? Is it deliberate caution to avoid fueling speculation? Is there any possibility that agencies know something they're not sharing? That early analysis of pre-conjunction data revealed something anomalous enough to warrant careful consideration before public disclosure? The last option, while it makes for compelling narrative, is highly unlikely for reasons already discussed. The distributed nature of astronomical observation makes cover-ups essentially impossible. Too many independent eyes watching, too many international collaborations, too many amateur astronomers capable of contributing observations. If something truly extraordinary appeared in the data, it would leak through professional networks, conference presentations, preprint servers, where researchers share findings before formal publication. The more probable truth is simpler. Agencies are waiting for good data before saying much of anything. They're conserving communication resources for when there's something concrete to report. They're letting the conjunction pass without amplifying what is, from a technical standpoint, a routine observational challenge, and they're probably hoping that when 3I Atlas reappears in November, it will do so predictably, allowing the science to proceed without the complications of public misunderstanding or sensationalized coverage. But hope and outcome aren't always aligned. And if the November reobservations reveal something unexpected, if the post-perihelion data shows anomalies that demand explanation, then the institutional silence of October 2025 will in retrospect look like a missed opportunity for proactive communication that could have shaped public understanding before speculation filled the void. We'll know soon enough which narrative emerges, routine confirmation of predictions, or something that forces a rethinking of what we assumed. Until then, the agencies remain mostly quiet. The technical databases update when they have new information, and those of us watching this unfold are left reading between the lines of what's said and what's not, trying to distinguish between meaningful restraint and simple procedural caution. We need to step back and see 3I Atlas, not in isolation but as part of a sequence, a pattern that's only now beginning to emerge from the statistical noise of cosmic observations, because this isn't just about one comet going through solar conjunction. It's about humanity's growing catalogue of interstellar visitors, objects that originated outside our sun's gravitational domain and traveled the vast emptiness between stars to pass through our planetary neighborhood. 3 confirmed detections in 8 years. 3 objects, each with its own peculiarities, each teaching us something about what exists in the broader galaxy, each raising questions, even as it answers others. And when you lay them side by side, Oumuamua, Borisov, and now 3I Atlas, patterns begin to emerge. Or do they? That's the question we need to examine carefully. Oumuamua arrived first, detected in October 2017 by the Pan-STARRS telescope in Hawaii. The name means scout or messenger in Hawaiian, and it certainly lived up to that designation by bringing messages that challenged our assumptions. Initially classified as a comet, then reclassified as an asteroid when no coma or tail appeared, then reconsidered again when trajectory analysis revealed it was accelerating in ways that couldn't be explained by gravity alone. That acceleration was subtle, detected only through careful analysis of astrometric data over weeks of observation, but it was real and significant enough to demand explanation. The most natural explanation for non-gravitational acceleration is outgassing jets of sublimating ice, acting like weak rocket engines. But Oumuamua showed no visible coma, no spectroscopic signatures of outgassing, none of the usual evidence that would accompany the gas production necessary to explain its acceleration. This discrepancy fueled intense debate. Maybe the outgassing was there but too faint to detect with available instruments. Maybe the composition was unusual, releasing gases that didn't create visible comas. Or maybe, and this is where R.V. Loeb entered the conversation with his controversial hypothesis, maybe it wasn't natural at all. Maybe it was a light sail, a thin sheet of artificial material pushed by solar radiation pressure, explaining both the lack of outgassing and the anomalous acceleration. Mainstream astronomy largely rejected the artificial hypothesis, considering natural explanations more parsimonious, even if they required some stretching of parameters. But the debate highlighted something important. We didn't fully understand Oumuamua. We still don't. It passed through the inner solar system and left before we could organize detailed follow-up observations, and now it's too far away and too faint to study further. It remains a puzzle, an object whose exact nature is still contested in literature. Then came 2I/Borisov in August 2019, detected by amateur astronomer Gennady Borisov using a 0.65-meter telescope he built himself, where Oumuamua was enigmatic and resisted categorization. Borisov was refreshingly normal. A comet that looked like a comet, behaved like a comet, showed a prominent coma and tail, exhibited outgassing consistent with water vapor and carbon monoxide, followed a trajectory explained entirely by gravity and expected non-gravitational forces. Finally, we had an interstellar visitor that matched our template. The relief was almost palpable in the astronomical community. See, interstellar objects can be ordinary. Not everything from beyond our solar system has to be weird, but Borisov carried its own surprises, more subtle than Oumuamua's, but significant nonetheless. Its carbon monoxide concentration was unusually high, suggesting formation in a particularly cold environment, colder than our solar system's comet-forming regions. Its carbon-to-oxygen ratio differed slightly from solar system comets, and its nucleus appeared to be surprisingly pristine, less processed by radiation and cosmic rays than we might expect for an object that spent eons traveling through interstellar space. These weren't deal-breaking anomalies, but they were reminders that even normal interstellar objects carry the signatures of their foreign origins, subtle chemical fingerprints that mark them as visitors from different stellar neighborhoods. Now we have 3I Atlas, displaying its own characteristic blend of familiar behavior and peculiar details. The retrograde orbit stands out immediately, moving through the solar system in the opposite direction to the planets and most other objects. Retrograde orbits aren't impossible. They represent objects captured or perturbed into backward trajectories, but statistically they're rare. The fact that one of only 3 confirmed interstellar objects shows this feature raises eyebrows. Is it meaningful? Does it tell us something about the dynamics of how interstellar objects get ejected from their home systems? Something about the geometry of stellar encounters that can flip orbital orientations? Then there's the orbital plane alignment. 3I Atlas travels nearly along the ecliptic, the plane defined by Earth's orbit and roughly followed by the other planets. Most objects in our solar system naturally orbit close to the ecliptic because they formed from the same flattened protoplanetary disk. But interstellar visitors should arrive from random directions, their approach angles determined by the geometry of stellar motions in the galaxy, rather than our solar system's internal structure. Having 3I Atlas arrive nearly in our orbital plane is statistically improbable, not impossible, but unlikely enough to note. When you combine retrograde motion with ecliptic alignment, you get an orbital configuration that's doubly unusual. Some researchers have calculated that the probability of this particular combination occurring by chance is quite low, perhaps a few percent or less, depending on the models used. Does this mean something is unusual about 3I Atlas? Not necessarily. Low probability events happen. Statistics tell us what's typical, not what's possible. And with a sample size of 3, we're nowhere near having enough data to distinguish genuine patterns from statistical flukes. But let's engage the thought experiment. What if there is a pattern? What if interstellar objects are systematically more unusual than random sampling would predict? This could point towards selection effects. Perhaps our detection methods preferentially find weird objects because weird behavior makes them more noticeable. Oumuamua's unusual trajectory and brightness changes caught our attention. Borisov's extreme outgassing made it bright enough for an amateur telescope to detect at great distance. Maybe 3I Atlas's retrograde, ecliptic-aligned path brought it through a region of sky we monitor more closely. We might be seeing a biased sample where the strange objects are more likely to get noticed and studied. Or, and this is where we tread carefully into more speculative territory, what if interstellar space is more dynamic than we assumed? What if the objects passing through our solar system aren't random ejecta from distant stellar systems, but participants in larger-scale galactic processes we don't yet understand? The galaxy rotates, stars orbit the galactic center in streams and groups, dense molecular clouds periodically perturb the Oort clouds of passing stellar systems. Could there be preferred directions, preferred speeds, preferred characteristics for objects that successfully traverse interstellar space? Could the act of traveling light years through the tenuous interstellar medium alter objects in ways that mark them as different from their solar system-bound cousins? These questions remain largely unanswered because our sample size is so painfully small. 3 objects, 3 data points from which to infer the properties of a galactic population that must number in the billions or trillions. It's like trying to understand Earth's ecosystem. By examining 3 animals chosen essentially at random, you might learn some interesting things, but comprehensive understanding would remain elusive. What we can say with more confidence is that interstellar visitors appear to be more common than we previously thought. A decade ago, before Oumuamua, estimates suggested we might detect 1 interstellar object per decade or century, depending on whose models you trusted. But detecting 3 in 8 years, despite observation being limited by technology, telescope time, and the sheer difficulty of catching these objects during their brief passages through the inner solar system, suggests the true population passing through our cosmic neighborhood is quite large. Perhaps several per year traverse the region we could potentially detect if our surveys were comprehensive enough. This revelation has practical implications. As survey telescopes improve, projects like the Vera Rubin Observatory coming online with unprecedented sky coverage and sensitivity will likely detect interstellar objects regularly. What's now a rare, exciting discovery may become routine observation, allowing statistical analysis that can actually distinguish patterns from noise. Within a decade or two, we might have dozens or even hundreds of confirmed interstellar visitors catalogued, enough to understand which features are typical, which are rare, and which genuinely demand explanation beyond natural processes. But we're not there yet. We're still in the era of individual objects carrying outsized significance, where each detection is an event, where every peculiarity gets scrutinized because the sample size is too small to confidently dismiss anything as routine variation. And 3I Atlas, hidden right now behind the sun's glare, represents our most recent chapter in this unfolding story. When it reemerges, if it reemerges as predicted, the data we gather will add to our slender catalogue of interstellar knowledge. The compositional analysis will tell us more about chemical variation in the galaxy. The trajectory refinements will test our understanding of dynamics. The structural observations will reveal whether interstellar travel affects cometary integrity in detectable ways. And if something about the post-conjunction observations surprises us, If some feature appears that doesn't fit the pattern established by Oumuamua and Borisov, then we'll have to expand our thinking once again, accommodate new possibilities, build models that explain not just one or two but three unusual objects. Pattern or coincidence? The question hangs in the air, unanswerable with current data, waiting for more observations, more objects, more time to accumulate the evidence that will eventually let us see clearly what right now we can only glimpse dimly through the noise of limited statistics and selection effects. The void between stars is speaking to us, sending messengers through our solar system. We're learning their language slowly, one object at a time, trying to distinguish signal from noise, trying to understand what the pattern means if there is a pattern at all. And somewhere behind the sun right now, invisible to our instruments, 3i Atlas continues its journey, potentially adding new sentences to this cosmic narrative, waiting for geometry to allow us to read them. There's something profound about not being able to see something you know is there. It's a reminder of limitation, of the gap between knowledge and observation, between confidence and certainty. Right now, we can calculate where 3i Atlas should be with impressive precision. Our equations place it within a few thousand kilometers at any given moment, which sounds imprecise until you realize that's pinpoint accuracy for an object tens of millions of miles away. We know, mathematically, where it is, but we can't see it. We can't verify. We're blind. Not because our instruments failed or our science is wrong, but because the universe's geometry has temporarily placed our target behind an obstacle we cannot work around. This situation, temporary though it is, offers a moment for reflection on what it means to be human in an age of space exploration and cosmic discovery. We've achieved so much. We've sent robots to Mars, probes to the outer planets, spacecraft beyond the solar system carrying messages for any intelligence that might someday encounter them. We've detected planets around distant stars, observed galaxies forming in the early universe, measured gravitational waves from colliding black holes. Our knowledge has expanded exponentially within a single human lifetime. Those of us old enough to remember a pre-internet world, a pre-Hubble world, a world where landing on the moon was the frontier rather than routine satellite operations. We've witnessed a revolution in what humanity knows about the cosmos. And yet, with all that progress, we still encounter moments of helplessness. A comet passes behind the sun, and we simply have to wait. We can't force observation. We can't demand that nature accommodate our impatience. We're constrained by orbital mechanics, by the speed of light, by the brightness of the sun overwhelming everything in its vicinity. These aren't technological limitations we can engineer our way around with better instruments or bigger budgets. They're fundamental constraints imposed by physics itself. No matter how advanced our civilization becomes, some things will require patience rather than innovation. There's a lesson in that for how we approach not just astronomy but existence itself. We live in an era that promises instant everything. Instant communication, instant information, instant gratification. The idea that we have to wait weeks for an answer, that we have to sit with uncertainty while geometry slowly shifts to favor us again, feels almost archaic. It's uncomfortable. It generates anxiety. We want resolution, closure, confirmation. We want the story to continue without interruption. But the universe doesn't operate on our preferred timelines. It unfolds according to its own rhythms, indifferent to our impatience. This is particularly poignant for those of us in the older demographic, those who've lived long enough to see how patience has been gradually squeezed out of modern life. There was a time when you mailed a letter and waited weeks for a reply, when you wondered about something and had to go to a library to research it, spending hours with books and periodicals rather than seconds with search engines. When mystery and uncertainty were simply part of experience, accepted rather than solved instantly. We've gained much through technological acceleration, but we've lost something too, perhaps a certain comfort with not knowing, a tolerance for gaps in information that weren't seen as problems requiring immediate solutions. The 3i Atlas conjunction brings the older rhythm back temporarily. There are no updates to check, no fresh data to analyze. Just the knowledge that on the other side of the sun, a cosmic visitor continues its journey, indifferent to whether we're watching. And we wait. Not because we lack the will or resources to observe, but because observation is temporarily impossible. The waiting isn't passive, though. Researchers are preparing. Observation campaigns are being coordinated. Instrument time is being coordinated. The moment geometry permits, activity will surge. But right now, in these late October days of 2025, there's enforced stillness. What does this temporary invisibility teach us about our relationship with the cosmos? First, that the universe is under no obligation to convenience us. Space is vast. Objects move according to gravitational laws that predate humanity by billions of years, and our desire to observe doesn't alter these fundamental realities. We're participants in a system vastly larger than ourselves, and sometimes that system positions things in ways that limit our access. Accepting this isn't defeatism, it's realism, a recognition of our actual place in the cosmic order. Second, it reminds us that knowledge is provisional and observation dependent. We're confident about what 3i Atlas is doing behind the sun, because our models have been tested extensively with other objects. But that confidence is different from certainty. If something violates our models, if some unexpected factor intervenes, we won't know until we can observe again. Science is an iterative process of observation, hypothesis, and testing. The gaps in observation are where uncertainty lives, and learning to be comfortable with that uncertainty is part of scientific maturity. Third, events like this highlight the value of patience in an impatient age. The conjunction will end. 3i Atlas will become observable again. The data will flow. Questions will get answered. This is inevitable, guaranteed by orbital mechanics with the same certainty that the sun will rise tomorrow, but it will happen on the universe's schedule, not ours. And there's something almost meditative about accepting that, about recognizing that some processes cannot be rushed, that answers will come when conditions permit rather than when we demand them. For the scientific community, the 3i Atlas situation also underscores the importance of preparation and coordination. The fact that major observatories have time allocated for November observations, that researchers have prepared analysis pipelines to process incoming data quickly, all of this reflects decades of experience managing observational campaigns around solar system objects. The waiting isn't wasted time, it's preparation time, ensuring that when the window opens we're ready to maximize what we learn. And what might we learn? Beyond the immediate question of whether 3i Atlas survived perihelion intact and whether its trajectory matches predictions, there are deeper scientific questions at stake. How does an interstellar journey affect cometary structure? Are there compositional signatures that distinguish interstellar objects from solar system natives? What can the population statistics of detected interstellar visitors tell us about galactic dynamics and planet formation processes around other stars? Each interstellar object we study adds a data point to our understanding of the galaxy as a chemical and physical system. The sun and its planets represent one stellar environment, one set of formation conditions, one chemical fingerprint. But there are hundreds of billions of stars in our galaxy, each with potentially different elemental abundances, different planet formation histories, different outcomes for what kinds of objects get ejected into interstellar space. By studying visitors like 3i Atlas, we're sampling that broader galactic diversity, learning what's typical and what's unusual across a much wider range than we could access by studying only our local solar system. This broader perspective shifts how we think about our place in the cosmos. We're not just citizens of Earth or even of the solar system. We're part of a galactic community of matter and energy, sharing the same physical laws and chemical elements, connected through the slow interchange of ejected comets, asteroids, and perhaps even organic materials that travel between stellar systems over millions of years. Some scientists speculate that life itself might spread through this mechanism, panspermia, the idea that microorganisms could survive on ejected rocks and seed new worlds when they eventually encounter suitable environments around other stars. Whether or not panspermia is real, the existence of interstellar visitors like 3i Atlas proves that matter does travel between stars, that stellar systems aren't completely isolated islands, but part of a connected galactic ecosystem exchanging material over vast timescales. This is humbling and exciting simultaneously. Humbling because it emphasizes how small and young our civilization is compared to these cosmic processes. Exciting because it suggests possibilities for understanding and perhaps eventually participating in processes operating on scales we're only beginning to comprehend. But all of that, the future discoveries, the deeper understanding, the expanding perspective, depends on observation, and observation depends on visibility, which brings us back to the present moment, October 2025, with 3i Atlas hidden behind solar glare, and all our questions suspended in the waiting. The silence is temporary. The answers are coming, and when they arrive, when the first post-conjunction images confirm the comet's position and condition, we'll have moved one small step further in humanity's gradual expansion from a species that looked up at the sky in wonder to one that can read the messages written in starlight and decode the stories that cosmic visitors carry across the void. The waiting is almost over. The next chapter of this story is about to begin. Early November will bring clarity. That's the promise of orbital mechanics, the guarantee that geometry gives us when all else remains uncertain. The Earth continues its annual journey around the Sun, moving approximately 1.6 million miles per day along its orbital path. This motion is slowly changing our viewing angle relative to 3i Atlas and the Sun, shifting the alignment that created the conjunction. Within days, perhaps as early as November 3rd or 4th, certainly by November 7th or 8th, the comet will have moved far enough from the Sun's position in our sky that telescopes can begin attempting reacquisition without pointing dangerously close to solar glare. These early observations will be challenging. The comet will still be relatively close to the Sun from our perspective, observable only during twilight hours when the Sun is below the horizon, but its scattered light still brightens the sky. Contrast will be poor. The comet might appear low on the horizon from many observatories, where atmospheric thickness degrades image quality. Initial detection attempts might fail, not because the comet isn't there, but because conditions aren't yet favorable enough for definitive observation. This is why observation campaigns are scheduled for mid-November rather than immediately after conjunction ends, giving a few extra days for geometry to improve, for the angular separation between Sun and comet to increase to more comfortable values. By mid-November, conditions should be ideal. Multiple observatories in both northern and southern hemispheres will have clear shots at 3i Atlas's predicted position in the constellation Virgo. The comet will be well placed for nighttime observation, away from solar glare, at moderate distances from Earth, allowing detailed study, and those studies will come quickly. Within hours of first detection, data will begin flowing, position measurements to confirm trajectory, brightness, estimates to assess activity levels, potentially spectroscopy to analyze composition if the comet is bright enough. What are astronomers looking for in these critical first observations? The priority list is straightforward. First, does the comet exist where predicted? If telescopes pointed at the calculated position find 3i Atlas within the expected error margins, that's confirmation that our gravitational models worked correctly through perihelion, that no unexpected forces significantly altered the trajectory. This is the baseline requirement, the observation that allows everything else to proceed normally. Second, what's the brightness? Comparing post-conjunction brightness to pre-conjunction observations will immediately reveal whether perihelion enhanced or reduced activity levels. A brightening would suggest increased outgassing from solar heating, possibly exposure of fresh icy material from below the surface crust. A dimming might indicate crust formation sealing the surface, or mass loss that reduced the amount of material available for sublimation. The brightness change, or lack thereof, tells a story about how the comet responded to its closest solar approach. Third, spectroscopy. If instruments can analyze the light coming from 3i Atlas's coma, comparing those spectra to pre-conjunction data will reveal whether composition has changed, whether new volatiles are now being released, Whether the ratios between different gases have shifted, whether that nickel signature persists or has evolved. Spectroscopy is the tool that lets us read chemical signatures, and any changes between pre- and post-perihelion spectra would provide direct evidence of how the comet's surface evolved during its closest solar approach. Fourth, structural integrity. High-resolution imaging, perhaps from Hubble if observation time proceeds as scheduled, will show whether the nucleus remains intact or has fragmented. This might not be immediately obvious in early observations if fragments remain close together, but over subsequent days, any splitting would become apparent as pieces separate along slightly different trajectories. No fragmentation would confirm the comet was structurally robust enough to survive perihelion stresses. Fragmentation would be interesting in its own right, offering opportunities to study the composition and structure of multiple pieces rather than a single nucleus. Assuming the November observations confirm that 3I Atlas survived perihelion intact and is following its predicted trajectory, attention will turn to tracking its subsequent journey through the solar system. The comet's closest approach to Earth is scheduled for December 19, 2025, when it will pass within approximately 140 million miles of our planet, farther than the Sun, so not particularly close, but close enough for excellent observational geometry. This will be the optimal time for detailed studies, when the comet is nearest to our instruments and moving against the background stars at a rate that makes it easy to track and photograph. Following the Earth flyby, 3I Atlas will continue outward, heading back toward the outer solar system on its way out of the Sun's gravitational domain. The trajectory will carry it past Jupiter's orbit in March 2026, not particularly close to Jupiter itself, but in that region of space. At that distance, with the comet receding from the Sun and cooling, activity will likely diminish as outgassing slows. It will become fainter, harder to observe, eventually fading into the background sky as it heads back toward interstellar space. But we'll be watching it all the way. Every observation adds data points, refines our understanding of how this particular interstellar visitor behaves throughout its solar system passage. By the time 3I Atlas fades from detectability, sometime in mid to late 2026, we'll have assembled a comprehensive observational record spanning more than a year. Its approach, its perihelion passage, its departure, creating a dataset that researchers will mine for years, extracting insights about interstellar object properties and behavior. This is the promise waiting on the other side of the current conjunction gap. This is what we're moving toward: clarity, data, answers to at least some of the questions raised by this cosmic visitor. And the remarkable thing is that we can state this with confidence even while we're temporarily blind, even while we're waiting in the gap. Because orbital mechanics are reliable, because gravity is predictable, because the universe, for all its mysteries and surprises, operates according to laws we've successfully decoded. Unless, of course, something unexpected has happened. Unless the ordinary explanations don't hold. Unless the November observations reveal something that challenges our confidence and demands we rethink our assumptions. This possibility, however remote, is why the scientific community waits with not just anticipation but a carefully guarded awareness that nature has surprised us before and might do so again. Will November bring confirmation and continuity? The reassuring discovery that 3I Atlas behaved exactly as predicted, that our understanding was correct, that the gap was just a gap and nothing more? Or will it bring disruption and puzzlement, observations that don't match predictions, anomalies that demand explanation, mysteries that deepen rather than resolve? We'll know soon. Very soon the geometry is shifting in our favor even now. The blind spot is closing. And within days we'll transition from waiting to knowing, from speculation to observation, from this strange period of enforced uncertainty to whatever reality emerges when we can finally see again. The reemergence is coming, the silence is ending, and whatever we discover when 3I Atlas returns to visibility will shape how we understand not just this one object, but the broader population of interstellar visitors, and what their presence in our solar system means for our place in the cosmic story. The waiting has been long. The answers are almost here. And in that approaching moment of revelation, when telescopes lock onto the comet's position and data begins flowing once again, we'll discover whether our patience was simply a pause in a familiar narrative, or the threshold of something that changes how we see the universe and our role in exploring its mysteries. The next observation could come any day now. The story is about to continue. Are you ready for what it might tell us?